Yeah. Hi, everyone. Welcome. My name is Bob. I'm the tech lead for the SDK platform on Settle. Okay.
Right. Do you need to be a bit closer to the microphone? Let's just see.
Can you hear me now?
All right, take one micro step closer again for me. All right, good.
Okay. It's going to be hard to live code from here, but we'll try to manage. So my name is Bob. I'm tech lead for SDK platform on Settle by PayPal. We'll try to talk about cracking Kotlin coroutines. And I know a lot of you have already been doing a lot of coroutines, but many of us starting with coroutines, we dive directly into flow or trying to move from RX into coroutines. And I'm here trying to get you into the thinking of coroutines first. So we have a lot of things to cover, and I expect you to have some familiarity with coroutines already, so this is not an introductory course or presentation. So we'll go quite quickly through the beginning, and then if we have times, we'll cover some streams as well. But this is mainly about coroutines and not flows or channels. And I do have some live coding, and I have some cheating, some helper functions for me because I have the device, as you can see. So instead of printing to the log, I'm printing to a text view. And before we know exactly what it entails to create a coroutine, just for reference, I'm using the view mirror scope until we actually gone through all that. So let's get cracking and start with suspension, which is essentially the most fundamental part of coroutines. Without suspending, coroutines would be more like a structured thread pool executor. It's a bit exaggerated, but essentially it is. And how suspension works is that in your coroutine, when you hit the suspension block, the coroutine actually creates an object, a continuum, puts the state of the coroutine into that continuum and puts it on a queue. So it actually pauses your coroutine. And then whenever the system and everything is ready, you can take that continuum and actually resume it. So think of it like a streaming video. You can pause the video. So each keyframe is a suspending point, or a game where you have a checkpoint and you can save the game and come back to the exact same state where the enemies are at the exact same locations. So it's actually dividing our coroutine to smaller units of code that we're not really thinking about. Often we think that the coroutine is the smallest unit, but actually the suspension breaks that unit into smaller bits. So let's just start by refreshing memory and see if you can figure out the order in this execution. Just take a few seconds and think for yourself, in which order will these numbers be printed? I'll give you a hint. The first one is 0. Otherwise, we need to have another presentation. So actually, when we go in here, I might have lost some of you here. If you did coroutines 2 years ago, then this wouldn't have happened. And now I might have lost a few more. And coming back from this one, we go in, we suspend again, and now the 7 comes around and goes back. I won't explain now exactly how this works, but in the end of the presentation, I hope you have a pretty good understanding in why all this happens. What we need to understand is that we actually divide our code into smaller units. And this continuation that I've been mentioning, it happens in the background. It's Kotlin. Every suspend function actually gets a continuum as its last parameter to continue work on it. We can have a manual hands-on as well if we call the suspend cancelable coroutine it's a function, and in the lambda we actually get the continuum. So let's see that in code. I also have the order here if you just want to prove that I'm not lying. Yep, still the same order. So this continuation, we see in the lambda that we get a cancelable continuation from this suspendable function. And then we print out, and then we can resume the continuation. We can fail it, cancel it, or with a success result. So we just run this continuation. We get an expected output. But if we actually change the order here, maybe we think that, okay, this is going to change the order of execution. But it's actually not. Okay, we know we can always add a delay. Then we force it. But the thing is, inside this lambda, it's like a letter on an apply. We're actually not inside the coroutine anymore. We're in the continuum. So we can't call suspending functions from here. What we can do is we can create, that would be a different example. We can create a thread in here, and we can make the thread sleep. If I can spell. And then we can actually see a usage of this continuum. So it's a rather nice bridge from the callback world into the coroutine world. So if you have a callback library and you need to bridge it, you actually can create your own suspending functions calling this directly. You maybe do a network callback and resume with the result. And in our coroutine, we just call a suspending function. So we got a nice bridge here between the words. And use the cancelable function, otherwise you won't play nice with cancellation. And as said, it's useful when bridging. But it is a suspending function, and all suspending functions needs to have a suspending function or a coroutine to be able to be executed. So where do we start? We start with our builders. And I actually excluded run blocking. These are the two essential ones for us as Android developers. So the launch creates a coroutine, starts it, and returns back a job, which is our reference from the outside world to that coroutine. And async creates a coroutine, starts it, and returns a deferred, which is a job, but you can wait for a value from inside the coroutine. So they're pretty similar. I'll use launch mainly in this, in all examples. And we don't actually need to understand how they can bridge from the non-suspending to the suspending, but we do have to understand that they need a scope. So they're extension functions to the coroutine scope. And it's a very small interface, only holding one reference to the coroutine context. And I've seen a lot of people being afraid of using and creating their own scopes. Don't be. Look at the view model scope that is used a lot. So every time you use a view model for a fragment, you create your scope for that view model and you use it. And when the fragment or view goes away and the view model goes away, the scope goes away. So there's no reason not to use them on a logical as your logical root, but don't overuse them. We'll see some pitfalls where we actually can go around how they're intended. But think of them as a logical root. So for a view model, the view model scope is logical. Maybe you have a Bluetooth module that needs to contain all of the logic and coroutine execution. then it's logical to have a scope for them as well. And since the scope only has one property, let's look at the coroutine context as well. And this is where most people get stuck in the beginning. We're reading too much into this context and the nice technical solution and using of overriding operators. But purely simplified, it's a hash map of context. And we can override. We need a context inside our coroutines because it's our rules. They are the rules to define how our coroutine is going to run. And we can override any value of the context. So we can override, for example, the name and any of them, creating a new context. And these are a few of the contexts that I'm mainly using. So the coroutine name is just naming your coroutine or your scope. And the execution or exception handler is an on-cut exception handler. We'll look into that later. Dispatchers, I know you all know about dispatchers. They define which threads you can run on. And the job, as you saw with the builders, is our reference back into the coroutine as well. And we'll look at the job indirectly first, looking into structured concurrency, which essentially is the meat of this presentation and what many people, especially as Android developer coming from RX, not truly grasp about this structured concurrency because we're looking too fast into flows or streaming or reactive. So this is something you really need to grasp to understand coroutines. So our builders are extension functions to the scope. And creating a new coroutine, like invoking launch, then we actually inherit the context. And we create a parent-child relationship. So a coroutine creates another coroutine. We have a parent-child relationship. And what is cool is that each coroutine awaits all its children before it completes. And this is quite different from the callback world, where we call a few things and wait for callbacks for all of them and then try to sync it. A coroutine does it automatically for us. Let's see if we can have some examples on this. So our first example is just we create a coroutine, and here I actually create a scope just to show you it's not dangerous. We create a coroutine from the scope, then we launch a child, and we launch another child, and then we just say that we're done. And this doesn't show as I want, because the parent coroutine actually runs its code, and then it waits. So I need to prove somehow that the line under here, that it actually awaits. That's where our job comes in handy. So it actually has a function, invoke on completion, that lets us know when the coroutine is done. So let's try that one instead and see if we can prove that it's waiting for its children. And as you see, it doesn't even matter if I go to a different thread on a different dispatcher, it still awaits every child of itself before completing. But you got to be careful using this function because depending on where live coding in an angle is always interesting. The invocation of this function depends on the last coroutine or run, so we can end up here from any thread. And here we also see an example of overriding the context. So here we create a coroutine. Next line we create a new coroutine, inheriting the context, all the rules from this one, but we override the dispatchers. Here we just create one, inherit everything, and don't override anything. And here we have a similar example. We first launch on a custom scope, then we launch a child on the view model scope, and then we just launch. Let's see if this one works. And essentially, here's one of the pitfalls from using scopes, is that the scope should be the root of your coroutines. So here we actually don't inherit from the coroutine outside. We inherit from the scope, which is our root. So this is why we should think about where to use our scopes, because launching from them, we inherit from the scope. We don't inherit from the outside world or what's going around it. It's just structure. And now we removed the scope, so we launch in the same scope. So we inherit everything, but here we actually pass in, override another job. So calling that one also fails. So now we're starting to see the mechanism between this parent-child relationship. It's actually the job that has that relationship for our coroutines. So passing in a new job, we actually create a new parent for the coroutine going in under, and this anonymous job doesn't have any relationship with the coroutine outside, because it's just an anonymous job. So let's look a bit at the job. It has a life cycle that dictates the state of our coroutines. We'll look at that briefly. And each coroutine has its own job. We said that the context and every context gets inherited by the parent, and job is one context, but it's the only one that isn't directly inherited. The inherited job actually becomes the parent of the coroutine we are creating. So this creates the hierarchy that we need for structured concurrency. And if we override the job, we create a new parent. So we're breaking the structured concurrency. Have a few short examples also on the job. And essentially what we see here is I created a job outside just to be able to share the state of the job outside. And then we call it again, we override it, so we know we're breaking, we're not confined to this scope, but we're looking at this job state instead. We create a child, and then we cancel to look at the state if it's changing. And we can see that it's changing, and the state diagram, just to have a quick glimpse at it, when you create a job, it goes into active. We can delay it, but automatically it goes into active or default. And then it runs its code and then goes to completing, which is a transitive state. So active and completing is sort of the same. It's just waiting for its children to complete before going into completed. And if it fails or cancels during active or completing, then it goes into a canceling state, still waiting for all its children to be done, to be canceled, and then goes into the cancel state. Another example is we looked at, and this is just proving with an outer job, that the view model scopes job from here, and when we launch on the scope, this job from the coroutine, we're checking if it's the same as the other job or if it's the same as the first child. And we can see in the output that this coroutine that I'm in is the same as the first child of the scope. And also on a job we have a join suspending function. It's essentially the same as on invoke on completion, but it's a suspending version. So essentially our coroutine works is after, or essentially that's not it. We need to do coroutine context, job, children, dot for each, and then we need to join each of them. So that's essentially what happens when the coroutine is done with its own job or its own code body. It will wait and join the other ones. And the join and await for async is sort of the same, but the await can give you a value back from the coroutine as well. And a big part of this structured concurrency, except for the waiting and doing things together, is cancellation. And the propagation, essentially canceling is we're throwing a cancellation exception in our coroutine. And when that happens, or when someone call cancels, at the next suspending of our coroutine, that exception gets thrown. So if we don't have any suspending functions in our coroutine, it will never get canceled. It will run through. The one waiting for cancellation will just have to wait for you. And the propagation is that when a coroutine ends in a cancellation exception, it will cancel all its children. So it propagates down to all children, grandchildren, etc. And by having the mechanism of throwing an error or exception, we have the chance to tidy up our coroutine. We can have a try-catch block, catch the exception, do some tidying up, maybe releasing a resource or something, and then we can rethrow the cancellation exception. And it's important to rethrow. I'll show you in an example. And it is collaborative. We need to have both rethrowing, and then we also need to have suspending functions, otherwise it won't work. And the rules of a coroutine that enters canceling state, so when someone calls cancel, it goes to canceling state, is that you can't call new suspending functions. You can't create new coroutines within that coroutine. We'll look at the exception that confirms the rules later, but that's, yeah, we need to go to the code. So here's first just an example of canceling, and this output should never be called. And it works. So since we have a suspending function, we can actually get the canceling. And as you see, I don't need to have any try-catch or handling the exception thrown. The cancellation exception is a nice one inside coroutines. It gets handled. Another more extensive example, we create one coroutine and then we create 3 children to that one, and we just cancel the second one just to see that it only is the second one that gets canceled. But if we actually move this cancel to outside, now we're in the parent coroutine instead. Then what happens is that is propagating down to all children that hasn't completed yet. So both the second and the third coroutine gets cancelled. And here we have the example of that we have to rethrow. So we can first run it and look at it and see that we actually have a try-catch block here to catch the exception. It gets thrown here that is suspending, and we can tidying up. Great, but if we call another suspending function, which I've defined down here, it swallows the cancellation exception. And if we run this example, we actually have broken our logic because we're not collaborative. So this code gets called, the tidying up never happens because we're swallowing the exception. And if we keep doing that, we can create flaky code, not only by not canceling. So if we call both of this, yeah, sure, it works well. So it works in my environment, on my phone it works. But if someone has a slower connection and the cancellation happens later, if we simulate that is a network call, then we actually get a different result from the same code, which is not good. So we need to be collaborative and always rethrow. And here's an example where we don't have any suspending. So we call cancel, but it keeps on rolling. And for this exact thing, we have a function that just yields to lets the coroutine know, like, here's an opportunity for us to actually break and suspend. And now we're canceling quite directly. And the last thing is on cancellation is on the scope. So we were talking about the view model scope and launching, and when we're done, we cancel the scope, and then we try to launch a new one because we came back or something. So canceling this, the rule was when we're in canceling state or cancel, we can't create new coroutines, we can't call suspending functions. So now that we canceled the view model scope, we actually broke the other buttons as well, because they are also dependent on the view model scope. So if we want to cancel something on a view model or on the scope, we need to call the coroutine context and cancel the children. Then we're going to cancel all children, but the scope still runs. And the other functions still run as well, so we can continue using the scope. When we cancel the scope, we can't create anything new on it. And we won't get any compiler errors. And exceptions, well, they're quite similar in how they work. As you might see, that they actually implemented in the exact same way that throwing an exception is the exception. The difference is that you can't use the cancellation exception because that will cancel. The exception throws, depending on if you're suspending functions or not, it will always throw. But it gives you the same chance of tidying up. You still have the rules that you go into canceling state, so you can't call suspending functions. And then we also have this special context, which is our exception handler. And we need to put the exception handler on our scope, because the propagation of exceptions is different from how the propagation of cancel works. The exception actually propagates to parent, the parent cancel all children, propagates to parent, grandparent, so everyone in the entire family, siblings, second cousin, third cousin, some aunt you never heard of, everyone gets canceled if you use a regular job. We can omit this by using a supervisor job, then the propagation will work exactly the same as cancellation. So you will catch the error and then just cancel your children. And here we create an exception handler that gets the context and the exception. I just print them for visibility. And how we add it to our scope is by the plus operator. So we can combine a lot of context. It's a similar setup as our cancellation, but we throw an error that is not an exception or a cancellation exception. So let's try this one. It crashes the app because we are on the view model scope and we don't have the handler on the view model scope. So an on-caught exception is still an on-caught exception. There's no difference going with a coroutine or any other code. So we need our handler to catch everything that isn't catched before. And it needs to be on the scope because as long as the job has a parent, it will rethrow. Even if you put a handler on every launch, it will rethrow until it hits the root. And here we see also in the output that we get error from where we throw directly to the parent and to parent, and the other ones are cancelled. So this supervisor job, we learned that we can actually prevent this propagation. And we can essentially do it like this, but not only do we stop propagation of the error, we also break the structured concurrency because we create a new job. So we should not do that. Instead, there's a function creating a supervisor scope for us that plays well with structured concurrency and actually creates the supervisor job as well. So if we run the code as it was, we still get cancellation and errors, but if we have the supervisor scope, that showing that it's null is that it didn't end with an error or a throwable, so it completed. And it's only the 2A, the child coroutine, that actually failed. And tidying up, here we have an exception again, and we need to do some suspending work to tidy up for some reason. And we'll try that, but we don't really get a result. Nothing happens when trying to tidy up. So the one exception that we can do if you really need to do a suspending call when tidying up, when in canceling state, is that we have with context non-cancelable. So this context can be run. We can create new coroutines. We should avoid it, but it is possible to actually do tidying up with suspending functions. So here we actually goes to another thread even and do tidying up. The last thing to touch on is the async exception. And it's a bit different because when we create the coroutine with async, it creates and starts it. So we see that we get the throwing, we get the catching, but we don't have a handler on the view model scope. So it's not an on-caught exception. When dealing with async, it actually is deferred to the output, which is deferred. So we need to call the await, and it actually throws in await instead of throwing elsewhere. And here we need a handler if we don't want it to crash our app, or a try catch swallowing. Oh no, we can't swallow here. So that said, we're way over time. Sorry for that. Thank you for staying. Just a quick one on streams. Come talk with me afterwards. I have more info. But the flows are built to collaborate with coroutines and cancellation and structured concurrency. Channels are not. Let's keep it at that to begin with. As you see, there's a lot of pointers, and I'll share this and the code later on. But essentially, the job is key. Honor the structured concurrency and grasp the suspending mechanism. That's my conclusion. Thank you.